So in the last video, we calculated the R squared for Meyer's original data, right? Trying to understand whether his data truly did show that more fat-soluble drugs were more potent. And why did we do that, right? Well, we did that because I want you to get used to doing maths with variation, right? Because nearly all statistical tests revolve around looking for sources of variation. But our goal was to see if we should believe Meyer's original result, right? Is this relationship real or not? And in order to do that, we were asking the question, is the slope of the line of best fit significantly different from zero, or is it basically horizontal, right? We want to know, does his data suggest that truly more fat-soluble drugs are more potent? And so what a scientist would want to do is get a p-value for that, because scientists like p-values, and when the p-value is very small, then they agree that there is a significant effect, right? Now, there's various controversies that have been going on for a very long time about p-values. We're not going to get into them. We're just going to assume that they're the best tool for the job. But let's sort of talk about them. How do you calculate p-values? Do you use R-squareds to calculate p-values? What even is a p-value, right? So the definition of a p-value is the probability of obtaining a test result at least as extreme as the one we observed under the assumption that the null hypothesis is correct, right? And that definition is like a lot of scientific definitions. If you know what a p-value is, this definition makes sense. And if you don't know what a p-value is, this does not really help you. But hopefully by the end of this session, you will have some understanding of what this means. All right. So can we use the R squared we calculated before to calculate p-values? No. One problem is that you can actually have a very large R squared, R squared near 1 with nearly horizontal data. So that's not going to help us. The other big problem is that any time you have two data points, the R squared is going to be 1, right? Because you can always draw a perfect straight line between two data points. And so if the R squared was somehow proportional to P, then every scientist would just get N equals 2 and be satisfied, right? In fact, we need some way to sort of reward using lots of data if possible. And so enter the F value. Okay, so the F value has an equation that on the surface might look almost exactly the same as R squared, right? R squared was the explained variation divided by the total variation. F is the explained variation divided by the unexplained variation, right? So we know how to calculate these already. You can't calculate an explained variation directly. You have to do the total minus the unexplained. There's a slight complexity in here. We're actually going to divide it by n minus 2, the unexplained variation. We're going to gloss over that for the moment. We're going to dig into it a little bit later, but we can already see, right, that if the n is very, very large, then of course n minus 2 is still going to be large. So we're going to divide the denominator of this equation by a large number, which will make the denominator small, and hence f will be big. Spoiler alert, big F's are good, all right? So as I say, we replace explained variation with total minus unexplained. We calculate those numbers just as we did before, right? Total variation is just how much the data varies from the mean. Unexplained is how much it varies from the line of best fit. We plug those values in here, we get F equals 1.2. And what good was that? What is that going to get us? Well, the beauty of the F value is this. We know its distribution when the null hypothesis is true. What is the null hypothesis? The null hypothesis in this case is that the values on the x axis were randomly generated, the values on the y axis were randomly generated, and so there's no relationship between x and y. And so we just go through and we calculate f when there's no relationship between x and y. We don't do it once, right? Here's our random x values, here's our random y values, we plot them on the graph, we calculate f, we put it in a histogram. Then we do it again because, sometimes there's a good relationship. It's random. So sometimes the dice fall like that and you get a good relationship and you get a large F value. But most of the time the F values are pretty small. In fact, most of the time the F values are almost zero. And so our histogram takes on a shape like this in this case. And here I'm going to just run this 200 times, 200 sets of random X and Y values. I'm going to calculate F, put it in a histogram, and you can see the shape the histogram is going to take on. Nearly all of the time, the F values are very close to zero. In fact, people smarter than me realized you didn't need to calculate F like this, that you could work under the mathematical assumption that you had run this test an infinite number of times, and what distribution should F take on, and it's this orange graph here. This is the theoretical F distribution. And so because of this, you know that most of the F values under the null hypothesis, again, when there's no relationship between X and Y, are very close to zero. And it's very, very rare to get large F values. It's very, very rare to get a good relationship. And so because you know that when there's no relationship between the data, that F values are small, you can then say that if the F value is very large, it seems unlikely that there is no relationship between the data. In fact, more than that, you can calculate the probability of F being as large as you measured under the null hypothesis, and that is the p-value, right? So it's literally just the area under this orange curve gives you the p-value, because you are saying that this is the probability of getting an F value this large or larger. And if that probability is very small, then it seems unlikely that the null hypothesis is true. I.e., if we got an F value of 100, well, what are the chances of getting that if there was truly no relationship between the data? And that's just saying the same thing there. So now you sort of have some idea of how linear regression works. Can you use it? Yes, you can, right? So linear regression is used whenever you want to see if one continuously variable measurement affects another continuously variable measurement. What is continuously variable? It means that, sometimes you might get a value of 1, sometimes you might get a value of 2, and theoretically you could get any value in between. So, for instance, does the amount of diesel particulates in the air affect lung volume in infants, right? Diesel particulates in the air, one day you might measure it as 10, one day it might be 1, it could be 1.1, it could be 5.893. Same with the lung volume. Some lungs are bigger, some lungs are smaller, some lungs are in between, so on and so forth. Does the amount of fat in a patient's diet affect the duration of their seizures? There's been lots of work about how different oils in the diet could affect seizures, right? Again, fat in the diet. Somebody could have very little, somebody could have lots, somebody could have a small amount in the middle, right? But you couldn't do are they vegetarian or not, right? That's not a continuously variable measurement. They either are or they aren't. The distance a patient lives from a hospital, and the effects on waiting time. These are linear regression type questions.